This video will introduce a concrete form to the Fock matrix in Hartree-Fock theory. So we've already been mentioning along the course of this chapter that the Fock operator is going to be equal to our one electron or core Hamiltonian operator plus the sum over all of our occupied spatial orbitals of 2 times the Coulomb operator minus the exchange operator for each of those occupied spatial orbitals. Where we have our one electron operator is going to be the kinetic energy plus all of the nuclear attraction terms, and this term for the mean field potential is going to be a sum over the electron's interaction with all other electrons. Okay, so we also mentioned that the Fock matrix, in terms of all of the atomic orbital basis functions, its matrix elements f mu nu, are going to be defined as the integral of phi mu star Fock operator acting on phi mu, which if we separate out a bunch of different terms here, is going to be the integral split up in terms of the core Hamiltonian operator plus the sum over all the occupied spatial orbitals of the same integral with 2 times the Coulomb operator minus the exchange operator. So if we do those substitutions and simplify things out, what we're going to end up getting is a few new terms where we have what's going to be called the core Hamiltonian matrix element h core mu nu plus the sum over all the occupied spatial orbitals of 2 times the 2-electron integral in chemists' notation for spatial integrals, mu nu AA minus mu A nu for the Coulomb and exchange integrals, where now we've defined the new core Hamiltonian matrix, h core mu nu, where each of those matrix elements is defined as the integral of phi star mu h1 phi nu, where of course h1 we can explicitly define as the kinetic energy operator -1/2 del squared 1, del squared being the second partial derivative with respect to x1, y1, and z1 added up, minus the sum over all nuclei, a equals 1 to m, charge of nucleus in number of protons, za over r1a, distance from the electron to the nucleus. And we can further break up the core Hamiltonian matrix into 2 components where we have T mu nu, the kinetic energy matrix, where we put in the kinetic energy operator, and the nuclear attraction matrix, where our operator there is going to be the negative sum over all nuclei, Za over R1a for that operator. So our core Hamiltonian matrix is actually the kinetic energy matrix plus the nuclear attraction matrix. So we might say the core matrix is the T matrix plus the V matrix. Okay, so using those kinds of definitions and doing the substitutions we've been doing thus far, we get that the Fock matrix elements are going to be f mu nu equals h core mu nu plus sum a equals 1 to n over 2, all of the occupied spatial orbitals, and then times the sum over lambda and sigma of c star lambda a, c sigma a, times 2 mu nu lambda sigma minus mu sigma lambda nu for the Coulomb and exchange parts there. So that's where we've taken into account how much each of these basis functions are contributing to each of the occupied spatial orbitals that we have. Because we don't necessarily know what the form of A is, but we know how each of these A's is represented as a linear combination of the basis functions, where this A is indicated as a linear combination of sigma, and this A is indicated as a linear combination, or sorry, this one of lambda, and then this one of sigma. So we got those 2 linear combinations, which result in a new double sum there. And we can also note that according to our definitions in the previous video, that this term that I'm kind of circling there is actually the definition of the density matrix elements. So in fact, the Fock operator can be defined as the core Hamiltonian matrix element plus the sum over lambda and sigma of the density matrix elements lambda sigma of the two electron integrals Coulomb minus exchange of mu nu lambda sigma minus 1/2 mu sigma lambda nu, where I believe we've taken care of the double counting problem here by just doing a naive double sum and not worrying about pulling out the 1/2 in front. Okay, so altogether, this set of the two electron integrals times the density matrix elements, this is overall what we call the G matrix. So the G matrix is going to be a sum from lambda equals 1 to k for all of our k basis functions, sum sigma equals 1 to k, of all of the density matrix elements, p lambda sigma, times the two electron integrals mu nu lambda sigma, minus 1/2 mu sigma lambda nu. So notice the mu and nu indices make it to the other side, whereas the lambda and sigma indices get what we would call contracted out, where they are summed over and the result compiled in sort of this aggregate on the left-hand side. Okay, and of course the typical two-electron integral, two-electron spatial integral in chemist notation, we remind ourselves that mu nu lambda sigma is equal to the integral over the coordinates of spatial coordinates of electron 1 and 2 of phi star mu r1, phi nu r1, electron 1 on the left, 1 over r1 2, phi lambda star r2, phi sigma r2, electron 2 being on the right. Okay, so this allows us to equivalently express our Fock matrix either as a function of the density matrix or a function of the coefficient matrix C, which represents all of our molecular orbitals. So there's a one-to-one correspondence between a given density matrix and a given coefficient matrix, or shall I say for a specific coefficient matrix, the density matrix is defined. We can do an arbitrary unitary transformation on the coefficient matrix and the density matrix stays the same. The only thing that changes the density matrix is actually changing the form of what these orbitals are. So we could either say the Fock matrix is a function of the density or of the coefficients, either way. So we're now trying to solve the nonlinear problem of the Fock matrix as a function of the C matrix times the C matrix equals the overlap matrix times C matrix times the orbital energy matrix. So this looks somewhat complicated and messy, but we can make it a lot simpler if we use the following simplification. If we had an overlap matrix, which was just a Kronecker delta or an identity matrix, if we had an orthonormal basis set, we would have an identity matrix for S, and then we could just, cancel it out, it goes away. If we have an orthonormal basis set, then we have FC equals CE, or C epsilon. So if we have an orthonormal basis set, in effect what we can do is find the coefficient matrix by diagonalizing F. So if we can do something such that we diagonalize this F matrix, then all that's going to be left over here is the C matrix and the E matrix. So basically the diagonal form of the F matrix is going to tell us what all the orbital energies are, and we'll be able to get all of these coefficient matrices as a result, and we'll know what all of the we'll know what all the molecular orbitals are. So in essence, once we get to an orthonormal basis set, diagonalizing the Fock matrix is basically our task at that point. So our task in the next video is to figure out how do we get to an orthonormal basis set, and then using that orthonormal basis set, how do we use that orthonormal set in order to actually solve our Hartree-Fock-Roothaan equations for our molecular orbitals and orbital energies.